So this is a quick redo of our lecture for chapters 8 and 9, which have been combined. The technology on campus doesn't allow me to use my laptop or record the lectures anymore, so I'll do a backup this way. So what is probability theory? It is the probability, it's probably something's going to happen. So it's a chance that something will happen. It's not guaranteed. Something could happen, maybe nothing will happen, but even that's a possibility. Okay, so probability, possibly chance of something happening. And so when we think of the chance of something happening, we could rate the likeliness of it happening as either 0%, which would be impossible, or if something was certainly going to happen, we could say it is certain at 100%. Okay, and then everything in between. So, likely is maybe like right here, 75%, halfway between the 50-50 and the 100. And unlikely, maybe we'd rate about 25% here, and so forth. And there's various levels in between that are anything under 50% is less likely to happen than to happen, right? Less than 50% chance. Anything greater than 50% chance, we might say, is more likely to happen than not, more than halfway. So these are all possible values, but what we've got to see is that if we're using percentages, a probability has to be between 0% and 100%. There is not a negative percentage chance, and you really can't say there's 110%. Some people will do that, but they're just, trash talking. 100% is the highest you can go. So when we turn these percentages into decimals, right, 50% divided by 100, we get 0.50. 0%, we just get 0. 25% would be 0.25, and 75% would be 0.75. This one's sometimes the hardest one to see. When you divide 100 by 100, you get 1. So when we talk about 1, that's the certain probability. So you'll see in some of our conversations, we'll be talking about 1 is the certainty. So we're doing things in relation to 1. Think of that as in terms of 100%. Probabilities can also be listed as fractions, so 0.75 might be something like 3/4 as a reduced fraction, but what we start to see is probability is about how many chances something has of happening divided by how many total chances of something. So if we say there's 4, this is 3 out of 4, this would be 2 out of 4, or reducing down to 1/2, and this would be 1/4 chance, right? And then this would be 0/4 of a chance. So that's another way of thinking of probability. And up here, 4/4 of a chance. So there's 4 different things that could happen, and maybe they're each equally likely. This is how we come up with the probabilities, and sometimes how we answer a probability with a fraction. Okay, again, they're going to want reduced fractions, so 2/4 we would have to enter in. If that was the answer, we'd enter it in as 1/2. And 4/4 we'd enter in as 1. Okay, 1/4 and 3/4 are already reduced. So with probability, here's the theory behind it. We do things called a probability experiment, and that's simply rolling a die, a 6-sided die, flipping a coin, see if it comes up heads or tails, grabbing into a bag of marbles and seeing what color marble we pull out. So it's tests of uncertainty, randomness. With these, we have our sample space. So if we're talking about flipping a coin, our sample space would be either a head or a tails. And if we do it a number of times, we would list, like, say we did it 3 times, we could get a heads, a tails, a heads. That's one possible outcome. Another one would be a tails, a head, a head. So we start listing our sample space in this sort of fashion. and we call the sample space S. S is all the different things that could happen for our experiment. This is our experiment of flip a coin 3 times. See what happens. And each one of these would be what's called an event. So events happen within the sample space, and each one of these is a potential event that could happen. And what we see is what the probability, so this might be we might say the event is getting 2 heads, and both of these have 2 heads, but they're 2 different ways of getting 2 heads, and there's probably another way, a couple ways. There's one other way, right? Heads, tails, heads, tails, heads, 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 tails, and I think that would take care of it. We would have counted all the possibilities of getting 2 heads with these 3 events. So it would be 3 out of however many possibilities there are. I'm thinking it's 6. 3, 2, 1. Yeah, there'll be 6. So there is a 3/6 chance of getting 3 heads. 2 heads. Flip a coin. Let's add to that. Get 2 heads. So we say there's a 3/6 chance or a 1/2 chance, or we could say, well, that's 50%, right? So this is all we're doing. When we add all the outcomes together, they all have to add to 100% or 1, right? So this we might list as 0.5, 1/2 or 0.5. Then the other events, which are getting like 1 head, getting no heads, getting 3 heads, so those are all the possibilities. They all have to add to 1, have to have 100%. Okay, so these are the basics. So now let's get into it. Again, what we're seeing here, all this is saying, is to calculate a probability, we just need a fraction. We need to count how many events are in the sample space that match what we're doing. Again, thinking back to the last one, right there, getting 2 heads when we flip a coin 3 times, we would say, well, the number of those events was 3. The number in the sample space, again, we didn't list it all, but we could go ahead. You could get a heads, 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 right? That's a possibility, 3 heads. You could get a tails, a tails, a tails. That's another possibility. And you could get 2 tails, which actually would be sort of the reverse of these. If you think of replace the heads with tails and the tails with heads, we would have 3 possibilities, starting with tails, head, tails. Let's do this as I said. There's an event. We could have a heads, tails, tails, heads, tails, tails, and we could have a tails, heads, tails, tails, heads, tails. So that would be getting 2 tails. Okay. So yeah, I don't know why I did 3, 2, 1. So there are total in this outcome 1, 2, 3, 4, 5, 6. See, did I count something too many times here? Oh, I counted this one twice. Why did I do that? Okay, so there's 3 here. There's that. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Actually, there's 8 things. Oh, we better back up. It's not 50%. This is 3 out of... Sometimes if I go too fast, right? It's not a 50%. 3 out of 8. That doesn't reduce. If you turn it into a decimal, 3 divided by 8. I should remember these. I used to be a loan processor, and those interest rates are always in 8. So you get where you remember all the 8s. Yeah, 0.375. I was thinking of something like that, but it's been a while. 40 years. There we go. which is a 37.5% chance. 3 here, 3 there, 2 there. Okay, so the probability of getting 2 heads, we counted there was 3. The number in the sample space was 8, so our probability is 3/8. That's all there is to calculating probability. What we did, though, we have to remember, is we assumed it's equally likely to get a heads or a tails. The coin is what we call a fair coin. One side's heavier, it might be more likely to come up something, more heads, more tails, or something like that. But fair coin, this is what we would do. Okay, so that's theoretical probability, the theory. In theory, this is how it's supposed to happen. So here's a couple examples. How many ways of rolling a 3 if you roll a die one time? Well, sample spaces, we can roll a 1, 2, 3, 4, 5, or 6. We got a little die here, right? See if I can do my 3-dimensional drawing. Not too bad, right? There's a 1, and on the other side is a 5. There's a 2, and the other side is a 4, because they all add to 6. I think, maybe 2 and then a 4, 5. No, I think they gotta add to 7, maybe. Anyway, this might not be an accurate die, but something like that, right? There's only 1 3 on the die, so there's 1. We counted one way of doing it. That goes in the numerator, and there are 1, 2, 3, 4, 5, 6 ways to roll something. So 1/6, and our probability as a decimal is 1666 repeating, or we could round that and say that is 16.7%. Remember to turn a decimal into a percentage, multiply by 100. Another event we might be interested in is rolling an even number. So that would be a 2, 4, or 6. There are 3 of those, right? So that's the number. That what goes in the numerator. There are still 6 total possibilities of what could happen. 1, 2, 3, 4, 5, 6. And so that rolling a die and getting an even number, its probability is 1/2, which is 0.5 also, or 50%. These are all correct answers. We just look which one does the system want. Do they want the percentage? Do they want the decimal? Do they want the fraction? Okay, so look for that. It's basic probability. This is really the same thing. Empirical probability, we might think of this as observed probability. And this is, we could put it in with sports. So recently the basketball stuff was going on, something called March Madness. We watch people shooting baskets maybe, and that would be an empirical probability. What's their probability of each individual player of making a shot? Well, what they do is they watch them and see how many shots did they take. 1, 2, 3, 4, 5, 5, 6, 7, 8. How many shots did they make? Well, if they're like me, maybe they didn't make any, or maybe they made 2. So then they would say, these were the shot, these were made baskets, and so we could then say that they made 2 out of 8 shots, which is 1/4. So they've got a 25% chance on any given throw, assuming that this is they're in the same spot, same type of shot. Let's say they're a 25% shooter, and so it also means, we'll see a little bit later, there's 75% failure, right? They don't make it 75% of the time, or if they shoot 8 times, they're not going to make it 6 of the times. 2 of the times they made the basket, so they're probably not like on the starting team, right? But that's what an observed, so right here, observed number of times that he occurs. Well, they made the basket 2 times. Total number observed, they shot on 8 times. So here we are, right? 25%. And again, we report probabilities either as a fraction, as a percentage, or as a decimal, depending upon what the question's asking for. Personally, I'll just let you know I like percentages. It's easier for me to work with. Okay, so we're getting into some table sort of stuff because empirical probabilities is all about really statistics, which we're going to get into a little bit later. But we go collect some data. So this is some data on whether people were married, never married, divorced, or widowed, and broken down by male or female, some kind of a survey. And then the way this becomes a probability, we've got these people in this group, and we're randomly going to choose somebody from the group, and then we can find a probability. What would be the probability of the event that a female is observed? Wait, let's see, what are we trying to find? Oh, find the probability of the person as a female. Okay, that's all. Person is a female. Well, that's here. There's all these different females. There's a total of 124 females out of how many people? A total of 242 people. So we see 124 goes there. That's the observance of females. This is the observance of all the people. 124 divided by that is about 0.51, probably rounded, 51%. We could do the same thing with the males. If we wanted to know the males, that would be 118 over 242. And watch, I can actually do this without calculating because the males are the complement to 100, right? If 51% are females, that means that 49% have to be males. And if you plug this in your calculator, you'll get that, rounded at least. So this would be the probability of getting a male. And that's all there is to probability. It's sort of counting. If they didn't give us this total, we would have had to add these together to get that total. In the homework, I think there's a few of those. But there we are. Okay. And this is what I was talking about, the probability of an event not occurring. Remember, we had 51% females, 0.51. If we subtracted that from 1, we get 0.49. So not a female or a male would be 49%. So that's exactly what all this is saying. So you can read through it, but it's a little wordy and such, but we could say the not getting the event is always 1 minus the probability. And remember this 1, what does it stand for? Multiply by 100, that's 100%. That's the certainty. This is whatever it is, right? And there's multiple ways. So it also works at the probability of the event. Maybe we know what the probability of not having it happen is. We could subtract that from 1. And then just remember this little prime means not E. So just a different way of writing it. So a lot going on here, but just a simple concept that total probability is 100%. So something happening, chance of rain is 20%, chance of not rain is 80%. We do this every day we watch the news. So here's another example. If you roll a 6-sided die, find the probability that you do not roll a 4. Now, you could count all the ways of what would we roll, a 1, 2, 3, 4, 5, right? So it means if you don't roll a 4, you get a 1, 2, 3, 4. Oh, no, you don't get a 4. You get a 1, a 2, a 3, a 5, or a 6. Okay, so that's 1, 6 plus 1, 6 plus 1, 6 plus 1, 6. A lot of calculation to do, but we could just come here and say, well, that's 1. What's the probability of rolling a 4? That's 1/6. 1 minus 1/6 is 6/6 minus 1/6, which is 5/6. We could have counted 1, 2, 3, 4, 5. So that's going to be 5/6 for this sort of thing because there's 5 out of 6. Okay, both ways of doing it. It just, in more complicated things, situations, sometimes this is a lot easier to calculate, especially if they give us this. We can get the probability of not E. Okay, or probabilities, A or B. Now remember, that's a union, as they show down here from our set theory stuff we did. So both, it's either A happens or B happens or both happens. Well, if we count everything in A, let's think of a Venn diagram. Here's A happening. and we count everything in B, what we've done is we've counted this middle region, this intersection. It got counted twice. It got counted with A and it got counted with B. So that's why we have to subtract it off, because we only want to count each event one time. So the probability of A plus B, and then we subtract off the intersection. So we'd have to somehow figure that out. Or we just be real careful what we count. Maybe when we count A, oh, I've already counted that part, so I'll just count the part that's in B, but not the part in A. I'll count these guys over here. So we'll use this formula sometimes. Other times we'll just be very careful about how we're counting. Okay, but that's, and if there is no overlap, this is what's called mutually exclusive. I took that slide out because it just makes sense that here's A and here's B. There is no overlap, so this part is 0, so we subtract 0, and I just left it like that. Just if there's no overlap, subtract 0. Well, that doesn't change anything. These are mutually exclusive, so we don't have to look at it as two separate worlds. It's just that if they are mutually exclusive, they don't overlap, then we don't have to subtract something, but we need that information. Okay, so let's do an example of what might be happening here. So we've got a group of 25 baboons. We're told that 18 enjoy grooming, 16 enjoy screeching wildly, and 10 enjoy doing both. So that's an overlap. If we want to do a Venn diagram, remember, here's those who like to groom. Here's those who like to screech wildly. And in the middle, we've got grooming and screeching wildly. And so when we go to fill this in, remember, always do this middle part first. There's 10 there that enjoy doing both. And then as we go, the 16 that enjoy screeching wildly, well, we've already counted 10 of them here, so there's 6 here. Those 18 who enjoy grooming, well, we've counted 10 of them here, so there's 8 over here. And then, remember, we've got to have 25 baboons. This is 8 plus 10 is 18, plus 6 more is going to give us 24. Oh, but there's 25. There's one baboon who doesn't like to do either. Just sits in the corner by himself real quietly. So we could do it this way, write it out, but now if one baboon is selected at random, find the probability that it enjoys grooming its neighbors or screeching wildly, one or the other, or both. And again, we sort of did this. We could say it's 8 plus 10 plus 6. Out of the total of 25, so we're just carefully counting, right? That's 24 out of 25. Or if we were to use the formula, which they'll do next, it is 18. Let's do it up here. There's 18 who enjoy grooming, there's 16 who enjoy screeching wildly, and there's 10 that enjoy doing both, so we'll subtract them off. If you do this, 18 plus 16 is 20, 34 minus 10 is 24. Again, all out of 25 total. And here it is. They do it that way. 18 plus 16 minus 10. So we can use a formula, or back here we could just be very careful about how we count. Okay, both ways work, and you can kind of see the connection. And the reason we had to subtract the 10 here up here is because we included it in both of those. Okay. Another concept, if two events are independent, it means that when one occurs, the other has no effect. So something like flipping a coin. We flip a coin once, it has no effect on what's going to happen on the second one. Whether we got a heads or a tails, the second one still has a 50-50 chance of getting either a heads or a tails. Rolling a die, it does not change the probability of the second event happening. So with these, we're looking at two events happening, not just one, two events. So there's a first event and a second event. When we've got two events going on, coming back, we're going to use something called the multiplication principle. So rolling a 1 the first time is a 1/6 probability. Rolling a 1 the second time is independent. It's still a 1/6 probability to roll a 1. Probability of rolling a 1 2 times, twice. And so we would say that is 1 out of 36. Okay. And as long as they're independent, that's all we got to do. And here's a couple examples. A roulette wheel, they put a little ball in there and it goes around and lands on a number or a color. So here's the layout: 18 black, 18 are red, 2 are green. Those are the numbers. 38 numbered slots, 1 through 36. They have the numbers 0 and 0, 0. What is the probability of a red occurring on 2 consecutive plays? So notice 2 different trials. First one has 9 out of 19 because there are 18 reds, so that's 18 out of 38, which gets reduced down to 9 out of 19, right? Divide both the top and the bottom by 2. There's a common factor of 2 that cancels out. So that's where the 19th comes. You might not have seen that. So then we multiply those together. 9 times 9 is 81. 19 times 19 is 361. Divide it and you get this decimal, or like I like to think of it, is 22.4%. Okay, so I can have a feeling for that. Getting 2 reds in a row. Here's another example. What's the probability of a baby girl being born versus a baby boy? Well, it's about half because it's either a girl or a boy. Not quite, it's pretty close. So the probability of getting 9 girls in a row, right? I'm going to have 9 babies, all of them being girls, would be a very small probability that you get a girl in 9 times, but that would be 1/2 to the 9th power, right? 1/2 multiplied by itself 9 times. We could just do it this way, which is reduces down to 1 over 512. If you take 2 to the 9th, right, you get 512. If you take 1 to the 9th, you still get 1. That's kind of cool. So that's how that's working. Okay, probability of getting a hurricane. Data tells us there's a 5/19 chance in any given single year, and I guess it's independent. Each year is a new situation. So in South Florida, what's the probability that you'll get a hurricane 3 years in a row? If this probability sticks, first year's 5/19, second year's 5/19, third year's 5/19, we multiply it together. Seems like a very small chance, right? About 2%, 1.8% of getting a hurricane 3 years in a row. That's why people, even with a bad hurricane in a year, they say, well, okay, at least the bad hurricane hit, probably won't hit again for a while. But that's what the probabilities tell us. Okay. Now, there may be changes. This may not necessarily be completely independent. These probabilities may be changing due to something called global warming, climate change. What's causing the climate change is up to, there's various theories, but I think you can say we see a lot of effect that we're having. We've still got so many humans. We are affecting our planet. So what we do matters. How did all that plastic get into the ocean? It wasn't a natural event. Humans are doing it. Okay, so we could also calculate what would be the probability of not having a hurricane, right? 5/19 is the probability of having it. Subtract it from 1. There's actually a 73.7, let's call it 74%, if you want to round it up, of not having a hurricane. And so it's less likely to have a hurricane than it is to not have a hurricane. But we could then take that and say, well, what's the probability of not having a hurricane for 10 years, right? right? So we take our probability, 4/19, and we raise it to the 10th power, because again, that would be 10 years of no hurricanes. And we see that there's actually about a 5%, 4.7% chance that that won't happen, that we won't have a hurricane, which, what does that mean? About a 95, right? 95.3 to be exact, of having a hurricane. In a 10 years, at least one hurricane in a 10-year span. So very likely that we would have that. Hopefully it would be a mild one. But anyway, so getting into dependent events and non-independent. Oh, well, we talked about independent. That was it. So dependent events are, what happens is they rely on the other one. So that the first one happening, right, changes the probability of the second one. Maybe makes it more likely, maybe makes it less likely. So when we multiply the first thing happening, that doesn't change. We just, it's just its probability. But the second one is now B is going to have a different probability because A happened. Such as like maybe the probability of rain and the probability of getting in a car accident. Well, when it rains, the streets are slipperier, so is maybe more likely chance of getting in an accident. So if it's rained, the probability of getting in an accident is higher than if it hasn't rained. Okay, so that's the type of thing we're talking. The second event is being influenced, is either being more likely in the case of rain and car accidents, or less likely. Someone says something that's not nice to you, and then what's the probability of you going to their birthday party? Oh, they said something not nice, well, I'm not going. So it could also decrease the probabilities, right? So it's just all those things happening. So here's we'll go through this. I thought okay, I haven't set this one up, so it's not working quite as I wanted. It's giving you the answer, but let's think this through. We've won a free trip to Madrid. That's in Spain, so they speak Spanish over there, right? And you don't. I don't. We've got 10 cousins. I've got at least 10. And they want to go with you because you get to take 2 people with you, right? 2 people get to come with us. And so they'd like to come on that trip. And so we put each of their name in a card, place a card in a hat, and select one name. So that's our first selection. You then select a second name without replacing it because they're already chosen, right? So that's going to change the probabilities in the hat. So for the first cousin to be selected, what is the choices? Well, there are 10 cousins, and we're not told till later 3 of them speak Spanish. So what's the probability of selecting 2 Spanish-speaking cousins? So yeah, if you're going to travel and you don't speak Spanish, it'd be good to have both of them speaking Spanish. I would just do that as a thing, kick everyone else out of the room and take the 3. But anyway, what we would do is, if we're doing it this route, maybe you don't want to get somebody angry at you. There's 3 of them that speak Spanish. There's 10 cousins, right? So that's this one here. Now that one of them has been chosen, what does the hat look like? Well, there's only 2 cousins that speak Spanish that are remaining, and there's a total of only 9 cards in there, right? 9 cousins in there because we've taken one out. That's what's happening, right? The first selection, since we didn't replace the card, has changed actually it's changed the sample space, right? There aren't 10, there's only 9, and there's only 2 that are Spanish speaking. So that's how we do it. So it's, instead of 3/10 times 3/10, this is what we get, right? 6/90, which is we only have a 6.7% chance of getting both Spanish-speaking cousins. Again, I would increase the probabilities by getting rid of the 7 who don't and only selecting from the 3 that do. But, this is a math book. They don't always come back with the best solutions for reality. Okay, here's another one. Again, it's kind of a thing. So we're going to select a person at random. We've got 5 freshmen, 2 sophomores, 4 juniors. Now this is one of those where to find the probability, remember we always need the total. They didn't give it to us. So we got to calculate it. 5 plus 2 is 7. 7 plus 4, we got 11 people. And this is where it often happens. We're selecting people. So it's a probability of getting 2 freshmen, the first 2, and the third is a junior. Okay, so again, the first one, freshman, we see here we've got 5 freshmen out of 11, but once we select one, the second selection is now only out of 10 people, and there's only 4 freshmen left. So that's that probability. When we go to select the next one, we've one selected, so there's now only 9 people left, but we haven't selected any of the juniors, so there's still 4 juniors left. We can multiply it and we get 8/99, which is going to be pretty close to 8%, right? Because 8 over 100 would be 8%. That's pretty close. About 8% chance of that specific drawing. 2 freshmen followed by a junior. Okay, conditional probability. That's what we did when we were doing this dependent thing. The probability of B given that A happened. So it's conditional because we know something happened, or we're assuming something's going to happen. If A happens, what's the probability of B? That's what this is all about. And so we read this as probability of B given A. And again, these are B and A are just events, things happening. So a letter is randomly selected from the letters of the English alphabet. So, how many? There's 26 letters. Okay, find the probability of selecting a vowel. How many vowels are there? Well, there's 5 vowels, A, E, I, O, U. We've got something given. That's a conditional that the outcome is a letter that precedes H. We don't have 26 letters, right? This is a change in the sampling space. How many letters precede H? Well, I need to list them out. There's A, B, C, D, E, F, G, H. Oops, precedes H. H is not included, so these are the letters we're going to be taking care of. 1, 2, 3, 4, 5, 6, 7 letters. So that's going to be our denominator. How many of these are vowels? 1, A is a vowel, E is a vowel. So 2 2/7. That will be our probability. So you see how when we're doing this conditional, what the condition is this second thing that happened changes everything, changes the sample space. So it's going to change the probability of the first thing happening. First thing happening, we would have said, okay, there's 5 vowels out of 26 letters. That would be our probability. But not for this is just the probability of getting a vowel out of the alphabet equals, right? But this is the probability with this advanced knowledge. Okay. And so, yeah, we restrict it to just these guys. And A and E are vowels out of the 7 letters, so 2/7. Okay, so leaving all that behind. Let's see how this works with a table. Assuming that these numbers are representative of all U.S. women ages 40 to 50, find the probability that a woman in this age range has a positive mammogram given, okay, so that's a conditional that she does not have breast cancer. So what this has done is, remember, it changes the sample space. We're not talking about this whole table anymore because we know the woman does not have breast cancer. This is the only part of the table that exists anymore. We don't have this because we don't have this, right? This is our sample space. Now, probability that a woman in this age range has a positive mammogram, that's this one here, again, these two are gone out of the total. So it's going to be 6944 divided by 99200. Okay, that's our probability. And that's what they've done, right? They took this one and this one. But again, if you leave them all there, it's, I like to say this is our sample space. Ignore everything else. And then these become relatively easy. You pull them out. If you leave the whole table there, it's too tempting to maybe choose this one and this one. Okay, that's, positive mammograms out of the total. But with the conditional, we know that this really doesn't exist anymore because this has happened. How do we know it happens? Well, because the book told us, right? So a lot of these with the math is, how do we really know, right? Because the test is supposed to tell us whether they have cancer or not. But over time, what they would do is a second test, and they would find, it was positive first time, but you really didn't have cancer. And so, that's why you get a second opinion. With these kind of problems, I just want to point out, get you thinking, these people here are at the greatest risk. They had a negative, so they think they don't have cancer when they do. So these are called false negatives, and they're damaging. Now it doesn't happen a lot, but if you're one of these 80 people, you've got the cancer going, but you think you're fine, right? That does happen with some of these tests because the tests are not 100% accurate. So you still have to watch things. And of course, then some people like me, I'm always thinking something's wrong with me. Since I was a kid, they said I was a hypochondriac, but I feel something, or and I always think, well, maybe it's a false positive. So we worry about it. I spent a lot of my life worrying too much about these false positives. Fortunately, I guess so far I'm still alive. It didn't really happen, but it can, right? So it just tells us, oh, this is the end of the road for us. So now you're ready to work through 8 and 9 together. I've combined them into one assignment, and then we're going to do some counting, which will involve a little bit of a probability in chapter 10, and then we're going to apply these sort of concepts into the statistics in chapter 11 and 12. So take care, and hope all is well, and we'll see you in class.